this packet reservation multiple access where, so we started to talk about medium access control techniques. We started to talk about the four different domains where we can do the medium access control, including space division multiple access, code division multiple access, time division multiple access, or frequency division multiple access. We also started to work or to talk about collision-based techniques. We tried to give you some idea about the motivation behind collision-based techniques when the collision happens. And we also started to talk about some reservation-based protocol where we try in some cases to combine the reservation with the collision-based techniques, similar to slotted Aloha and using slotted Aloha together with some reservation to try to also overcome the high collision rates for the Aloha protocols. So the last thing we tried to cover is we tried to get rid of the overhead during the reservation phase. We said that for reservation techniques, reservation-based techniques, we have to have at the beginning like some overhead to try to perform the reservation phase. So during the reservation phase, we ask the nodes to broadcast or to announce or to declare their needs or their requirements to transmit, and then based on this information, we try to reserve resources for the next super frame, right? And then after we finish this super frame, we ask the nodes again to provide their requirements, and then we do this again and again. One example we talked about for the reservation phase is actually to use slotted Aloha for the reservation. And we said that we can have like some K many slots where the nodes can contend to send some short mini frames to report what they plan to transfer. What's the requirement of transmitting any data from their side? Chances are some of the nodes will not have anything to send, in which case I don't have to waste my resources. And this was the case for the TDMA and FDMA, where we reserve resources for nodes and nodes have nothing to send. So we try to avoid this by having a realistic expectation during the reservation phase where we only reserve resources when they are needed. Okay? And then we talked about the packet reservation multiple access, where we tried to get rid of the reservation phase altogether. And we said that the assumption here is that the nodes first contend, and once a node grabs a frame or grabs a time slot, it can reserve this time slot until it has nothing to send. When it has nothing to send, then I release that time slot and put it back in the pool of available time slots, and then other nodes will contend on this, and so on. So for this type of reservation time division multiple access, reservation time division multiple access here tries to use the combination of TDMA together with some contention using a modified Aloha protocol. So here we assume that each node will have up to K time slots to reserve, up to. This is the maximum, okay? So all the nodes, they have to report. In that case, the reservation phase does not use a slotted Aloha in that case. The reservation phase has N many slots. So all the nodes, they have to report. If a node does not report anything, I assume that the K here is 0 for that particular node, or in other words, the node has 0 time slots to use for traffic, okay? But in general, each node has up to K data slots it can reserve. So we assume that we have a network is divided into two categories of nodes. There are nodes that have higher priority, these types of nodes, they reserve the time slots beforehand. So in which case, the advantage of these types of nodes is that the delay that they incur is deterministic in that case, right? So whenever you have a guaranteed reservation, then you can guarantee the delay. You can guarantee your quality of service. صح ولا لا? Right? So in Aloha, we cannot guarantee any specific behavior or delay. Why? Because you can send your traffic suffers from collision. You send again, you suffer from collision. So you don't know. You don't know what type of delay you will go through at this point of time, right? But here, these high priority nodes, they can reserve up to K time slots, K data slots. And they declare this in the reservation phase. And the reservation phase in that case does not use by any contention-based or slotted Aloha. So here, the reservation phase is composed of n many slots. So all the high priority nodes, they can reserve. And in general, a node can reserve 1 slot, 2 slots, up to K time slots, right? So there is a chance that some of these slots will still be available. So we use these slots for low priority nodes. These low priority nodes, they have to contend on these time slots using some type of slotted Aloha. So again, this requires arbitrator or a centralized node to conduct this type of reservation. So here at this point, exactly, again, the arbitrator will announce that these slots during this super frame, these slots are reserved for these particular nodes. So only these particular nodes are allowed to send in these time slots. Okay? So each node will send in its K slots, and it sends 1 frame, 2 frames, depending on whatever the node reserves in advance. We end up with some empty time slots. We don't know the numbers, right? We don't know where they are, in which case the remaining nodes, which we call them low priority nodes, they will contend on these time slots. So for these nodes, because of the fact that they contend and there is some possibility of collision in these time slots, so some of these time slots might end up with some collision, right, from multiple nodes. In that case, these nodes, they suffer or they go through or they encounter variable delay, right, or undeterministic delay, right? That's why we call them best effort, or we call them low priority nodes. These low priority nodes, they go through what we call a best effort service. Best effort is like, I will try to serve you as much as I can, but I don't have any guarantees. Okay? Sometimes all these time slots are reserved in advance, in which case, in this particular super frame, the low priority nodes they cannot send anything. They don't have any slots available for contention. Okay? So, so this actually summarizes the collision-based techniques and the reservation-based techniques. We have 2 other types of medium access control techniques. One is the collision avoidance, which is used for ad hoc, and the other one is polling mechanisms. So we'll talk about this. In assignment 2, I actually will get to implement some of the techniques that we talked about, including the slotted Aloha and TDMA and all of these things. We'll develop some of these techniques as part of assignment 2, and you will get to measure the performance and the throughput efficiency and all of this. Okay. Type for the MACA protocols, or multiple access with collision avoidance, this is mainly used for wireless systems and not all types of wireless systems, ad hoc in particular. Because in ad hoc networks, we suffer very frequently from the 2 famous problems that we talked about, the hidden terminal problem and exposed terminal problem. And we suffer from many other scenarios that we didn't even discuss, And we'll discuss some of these scenarios now. So with collision avoidance, what we try to do, again, we cannot eliminate collision, we cannot avoid it completely, but we'll try to do certain strategies to reduce them or to try to avoid these types of collision. And one of the techniques is what we call RTS-CTS, or request to send and clear to send. Has any of you heard about this or studied this at some point? Okay, and sometimes in network 2 we cover this part. So, so using the RTS and CTS here, we use like short signaling frames. These short signaling frames, they try to announce, okay, throughout the network that there is some type of transmission that is going to happen. And the idea of this is that using these short frames, we achieve two things. First, because these frames or these short frames are very short, the possibility of collision for these short frames is low, okay? But they are used, more importantly, to inform all the nodes around that, you know, there is one node wants to send and another node is intended to receive a frame at any point of time. So by sending these short frames, we are informing all of them that, you know, there is something going to happen. So if you hear RTS, then you know that this sender wants to send to this receiver, then you abstain from doing anything, okay? If you don't hear RTS, but you hear CTS or clear to send, you also do the same, okay? So the way it works is as follows. So RTS, the sender sends this request as a short signaling frame, okay, to inform, to announce in the network that I want to send a frame, this frame, to a particular node, okay? So this RTS is going to be heard by the nodes around it, okay? So the nodes around it, if none of them is the receiver, then okay, they will abstain from doing any activity until the data is transmitted. So in that case, they go into a phase of what we call NAV, or network access vector. For NAV, these nodes that hear RTS, if they are not the receiver, then they go into NAV phase. NAV phase is that they estimate the time required for sending CTS and data and acknowledgement, and all of this time will be a silent time for them, okay? So this helps of course, during this time, by the way, they also do sensing. They also do carrier sensing, right? So we talked about carrier sensing, but as we said, carrier sensing does not eliminate the hidden terminal problem, right? We talked about this. So despite the fact that we use carrier sensing, we cannot avoid some specific scenarios like hidden terminal problem and exposed terminal problem. So with these types of RTS, CTS, we'll see about how we can try to avoid the hidden terminal problem and exposed terminal problem, okay? Type. So when we send RTS, there is the receiver and there is others. Others, as we said, others will go to NAV, right? The CTS will have to send clear to send. Clear to send is like, I'm ready to receive your transmission, okay? And we see that sometimes you don't hear RTS, but you hear CTS. I mean, for others. So if others, they didn't hear RTS, but they hear CTS, then they also go to NAV. بالضبط. يعني example for this is the hidden terminals. بالضبط. كلامك مظبوط. تمام. So when I send CTS, if the receiver receives this CTS, then the receiver will, the sender. If the sender receives the CTS, then the sender will be informed that the receiver is now ready to receive its transmission, so it will send the data. There is a chance that you don't hear RTS, you don't hear CTS, right? But again, you do sensing and you discover that there is transmission happening. That's possible also. So in some cases, you don't even hear CTS, you don't even hear RTS, but you sense and you see that there is some transmission happening. Again, if you are not intending to send at this point, or if you are not the receiver, then you will also go to nav. So you go to nav if you hear RTS, you hear CTS, or you hear the data, any one of them. But these two phases, during this time in particular, you try to avoid any node from sending anything. And remember, during this time, we have used very, very short frames, RTS and CTS, which طبعا there is a possibility even you can have collision in RTS or you can have collision in CTS, right? But because they are short frames, supposedly the collision will be less probability. طبعا there is this data interframe spacing or short interframe spacing. You don't need to know the real reason behind it, but these DIFS and SIFS, or short interframe spacing, these are used to overcome the hardware limitations, because sometimes you have to switch from receiver to transmitting and from transmitting to receiving. So especially if you are here, if you are a receiver node, then you have to listen to RTS and send CTS. So the hardware cannot send and receive at the same time, and in many cases you need a short interframe spacing to overcome the hardware limitations. So in all cases, these are in the nanosecond level, and usually they are negligible. Low SIFS. The IFS is a little bit significant, and usually this is at the beginning of the frame, at the beginning of the transmission frame, right? So this happens at the beginning to allow for any clearance on the channel. If there is any residual transmission on the channel, it will clear out before I start a new phase of transmission by sending RTS. The short interframe spacing is usually to overcome the hardware limitations. From sending to receiving or from receiving to sending. طبعا after transmission, we still need acknowledgement. Why? Because despite all of this, collision might still happen, right? In which case, the receiver may not receive the frame successfully. In which case, it will not send, or it sends an acknowledgement, or it sends a negative acknowledgement, or it does not send either. In which case, the sender will time out because it does not receive the acknowledgement on time, and it declares this frame as not transmitted, and it will have to repeat the whole thing again. RTS and then CTS and then واضح كده؟ طيب, there is different variations of this MACA protocol. There are different variations for this MACA protocol, and some of them they are implemented in IEEE 802.11, because as we all know, 802.11 it works for infrastructure based and ad hoc based as well. So you can use مثلا for Wi-Fi direct, you can use it for ad hoc, right? So the MACA protocol, it's optional as part of 802.11 protocols. So the developer can choose to set the MACA protocol enabled or disabled. In which case, if it's enabled, then use RTS CTS. If it's disabled, then the only thing you do is carrier sensing. That's it. You do carrier sensing for collision avoidance, but you don't use RTS CTS. واضح الكلام؟ So how does RTS CTS help in avoiding collision, and particularly help with the hidden terminal problem and exposed terminal problem? As we said, that for the hidden terminal problem, if A wants to send to B, right, A will send, and the transmission domain of A includes B, okay, but C does not hear that, right? C does not hear that. So during the transmission of the frame, remember that the frame is long. It may take like 100 milliseconds, 200 milliseconds. It's long, right? So if C does not hear that during this 200 millisecond, which in networks this is very significant, say C actually does not hear, so it may try to send, and the collision happens at B, right? So we'll see بقى with RTS and CTS, what will happen is that A will send RTS. Of course, again, RTS is the transmission phase for this goes all the way to B. C does not hear that. But the good thing is that B will send CTS in that case. And again, RTS and CTS, we're talking about a few nanoseconds, right? Few nanoseconds. So C in that case will not hear RTS, but it will hear a CTS. So CTS will go to nav. Or C will go to nav. So node C will go to nav in this case, and it will abstain from transmission, right? And of course, CTS has the information about the frame in terms of frame length, right? And the transmitter and the receiver. Transmitter address, receiver address, and the frame size. So from this, C can estimate the duration of time where it has to go to nav. Okay? واضح كده? So in that case, again, hidden terminal problem is taken care of by using the RTS-CTS protocol or the MACA protocol. تفضل.
Can we assume that this clear to send is mean? Like C maybe it will send RTS. We'll assume this clear to
صح.
send is for him.
لا ما هو احنا قلنا ال RTS وال CTS they contain 3 pieces of information: transmitter address, receiver address, and frame duration. ماشي؟ ممكن CTS, I'll go with what you say. So CTS, in which case C will send RTS, okay, before it hears CTS. صح؟ This is what you are trying to say, right? So there are 2 possibilities here. One is that RTS will collide with the CTS from B. Okay, they will both مثلا collide. They happen at the same time. So or B will send the CTS and it will go to A, right? In which case A will receive successfully CTS, right? And then it will try to send to B, and C will send RTS at the same time. So there is a chance, or there is a possibility that A will try to send to B a frame, and at the same time C sends a new RTS before it hears a CTS, right? That's also a possibility. ماشي? The possibility here is lower, but it's there. And we never claim that RTS-CTS eliminates collision altogether. So it's still, if there is any RTS that overlaps with a frame transmission, that's also a collision. There's no question about this. But again, because we assume that these are short frames, so transmission and processing of these short frames happen in nanosecond level. So that reduces the possibility of collision, because we can very fast inform as many nodes as possible around that there is a transmission happening, and if they are informed, then they abstain from doing anything. They never send RTS, they never send CTS or anything, right? طيب, exposed terminal problem, as we said, it happens based on the fact that B, in that case, B is trying to send to A, not the other way around. And C is not part of this at all. C wants to send to another node here, right? So supposedly that, as we said, that C is not actually involved in this transmission, because remember, the collision happens at the receiver. So if B wants to send to A and C wants to send to D, right, then that should happen concurrently. There's no problem with this. There's no conflict, right? But if we're not using the MACA protocol, we lose the opportunity for transmission. Why? Because when B tries to send to A, the transmission domain contains C. So C will hear that B is actually sending anything, sending a frame, right? So in that case, C will abstain from transmission, and it wastes an opportunity of transmission. And that's what we call the exposed terminal problem. So now, when B sends RTS, okay, C will be informed. On an RTS, we have we have three pieces of information. We have the sender, we have the receiver, and we have the frame, right? So in that case, C may in fact recognize that, depending on the protocol, may in fact recognize that B is sending to A, and I don't know whether I send or not, right? So in that case, B may wait a little bit to see whether it hears CTS or not. This is very important because if it hears CTS, then it interleaves with the transmission, and it may cause collision if it tries to transmit. But if C does not hear CTS, then it realizes that both the transmitter and the receiver, they are far away from C, and then it may actually try to send in that case. Okay? So if it hears RTS, then it waits for CTS. If it doesn't hear CTS, then it may decide to opportunistically send. But if it wants to be conservative, then if it hears RTS, it should also nav. It should also go to nav. And that's why we said that there are different variations of the MACA protocol. Some slight variations of the MACA protocol, they include these types of scenarios. So C, if C now hears RTS but not CTS, what should it do? Right? So it has two options. It may in fact try to send, because since it does not hear CTS, then it knows that it's not part of this transmission, and if it tries to send, then it will not interfere with this transmission. So it may be aggressive and try to send at that point, right? If it sends to D, then it's fine, everything is fine, right? So there's no issue with this because it doesn't hear CTS. Or it may, regardless, it may blindly decide that, okay, so even I didn't hear CTS, I will not send just to E to be on the safe side, right? Because the only way you know deterministically is that you have to have that location-based protocol. You have to know the location of every node in order to decide whether you are going to interfere with this transmission or not. So the only way is to have location-based technique together with MAC. So here, you may decide either or, right? And different variations, they exist as part of the MACA protocol, right? So at least RTS and CTS, they give you more information to decide whether you want to opportunistically access the channel during these types of scenarios, or you abstain and you take the conservative approach. So this is the finite state machine for the MACA protocol. Who here is not familiar with finite state machine? You know the finite state machine? You're not familiar with it? So finite state machine is a way for modeling a scenario based on states and state transitions.
It's used
right?
in digital logic?
It's used in many disciplines. It's used in everywhere, right? Finite state machine is used in Markovian, Markov state machines. It's used in mechanical engineering, in chemical. It's used in many things. So it's very simple. So you can model a system based on states, certain states. You can give name for the states, and then you can transition from one state to another based on event. Okay, and based on this event, you take an action that takes you to a different state. It takes you to a different state, right? So, so if you are in a particular state and there is an event happen, then you take an action, and then based on that, you can transfer to another state, or you can actually loop to the same state, right? So the action does not change the state, okay? So that's a way of modeling the functionality of any system. It's one of the powerful ways for modeling the functionality of a system. So for the particular protocol that we're talking about, this is the finite state machine for the sender, and this is the one for the receiver. So the sender in normal case will be in the idle mode, waiting for what? Waiting for a packet to come from the upper layer. Which layer are we here? This is which layer? لا احنا مش physical. MAC layer أو data link layer يعني. هنا احنا MAC layer, right? So we are waiting for a packet to come from the network layer. Then we extract the network header, and now we have a frame that we need to transmit, right? So if we are in the idle mode and we receive a packet ready to send, then what we do is that we can send RTS, and we move to another state saying that we are waiting for the clear to send or waiting for the receiver to be ready for receiving our frame, right? So when I send the RTS, then I wait, right? And there are two possibilities here. I wait for CTS and I receive it, or I don't receive CTS. What is the possibility of not receiving CTS? Because RTS was never delivered successfully, either because of channel error or because of collision or anything, right? So in that case, I will time out. When I time out, there is a chance that I send RTS again and I stay waiting in the same state, right? So if I receive CTS, then I go to I send the data and I go to another state called waiting for acknowledgement. If I receive the acknowledgement, then the whole cycle is done, and then I can perform this logic again and again and again. Okay? Again, if I time out, I send RTS again and I stay in the same state. Receive CTS, then I go to wait for acknowledgement. And if I don't receive the acknowledgement or I receive negative acknowledgement, when do I receive negative acknowledgement? The data was transferred, was delivered to the receiver, but the receiver received some parts in error, right? Okay? So in that case, the receiver received the frame, but received it with some error. So depending on whether you are using error correcting codes or error detection. If you're using error detection, then the only thing you could do is that you send negative acknowledgement asking the sender to retransmit. That's the only thing you can do. In wireless, and in some cases in wireless, we use error correcting codes. Okay? So even if there is an error, we can recover this error at the receiver. We don't have to send negative acknowledgement. That happens in certain cases, right? And in that case, we don't even have to send negative acknowledgement. We send positive acknowledgement in that case, even if the frame arrives in error. Again, this is ده تفصيلة صغيرة يعني, but that's what usually happens. Or we don't receive acknowledgement altogether. In which case, if we don't receive acknowledgement altogether, then we go here, we send RTS and we send RTS again, and we go to wait for CTS. It's like we are repeating the whole transaction again. Okay. If we receive acknowledgement and we don't have any other frame to send, we go back to idle. واضح اللوجيك؟ يعني simple يعني. The only thing we didn't talk about is this. Okay. So this will appear here. So the receiver is in idle state until it receives the RTS. If it receives RTS, so RTS received, we send CTS. That's fine, right? Or if we are waiting for receiving the data, and then we have if we wait for the data at the receiver side, and then we receive another RTS. Okay. Under which scenario this will happen? Now we are waiting for the data already, but we received RTS from another node. اللي هي hidden terminal problem مثلا. ماشي? In which case if we are waiting for data, but we receive RTS, this is exception. This is exceptional case, right? In that case, we send receiver busy. This is what we see here. Because we cannot deal with two transmissions at the same time. I'm engaged in one transmission already. I'm a receiver for one transmission already. I cannot engage in another transmission at the same time, صح? So in that case, we send receiver busy, and that's what we see here. So this receiver busy, the sender will receive it, and then the sender will say, okay, so I will stay in idle until another transaction starts after DIFS, right? And then I will try to send RTS again and repeat the whole thing again.
How many senders the receiver can deal with in the same time?
One.
Only one.
Yes.
What you said, he is waiting for something.
هو waiting for the transmission of this particular sender, but it receives from another sender,
Yeah.
so it has to send busy signal. خلاص busy. I'm busy. I'm busy with the current transmission. I cannot deal with two. I can deal with only one. واضح كده؟ So it sends this RX busy so that it avoids dealing with two. معناها it deals with one only at a time. اتفضل.
Send RX busy to all RTS sender.
Send ايه؟ RX busy.
To all.
هو when it sends RX busy is similar to RTS and CTS. It has all the information. It has the sending, which is in that case the receiver address, and it has the receiver, which is the sender address.
So all senders will hear it.
All senders will hear it, but this one will be informed.
So only one will go idle and the other one will send.
Right, but the other one will go to nav أصلا. The other one will hear it. اللي هم others, right? They know that they are not part of this engagement أصلا, صح? So the sender, that its address exists in the RX busy frame, will be informed that, okay, the particular receiver that I'm planning to send to is busy currently. So I have to go to idle until everything is done, and then I try another transaction, DIFS, and then I go to RTX and perform the whole thing. Others, they are not part of this, so they go to nav برضه. Right?
There is no sort of
تفضل.
queuing or.
Yes, of course, queuing is not part of this. But of course, يعني if the sender has multiple packets coming, so there is a queue here. The sender has a queue, right? So if it does not go to idle as long as it has data to send, right? يعني if I go here, actually the acknowledgement, if I receive the acknowledgement and I have packet to send, I go here directly. If I receive acknowledgement, I may actually get a packet and send the RTX and go to here all at the same time, right? If I have data in the queue. But here we assume that if we receive the acknowledgement, we go to idle, right? Because we don't have data in the queue. But if you have data in the queue, then you fetch it, you send RTS, and you perform the whole thing again. Okay? Any حد كان عنده سؤال؟
Doctor, on the receiver side, isn't suppose the hidden node can hear CTS?
The hidden node can hear CTS. Yes, we said that hidden node will hear CTS. But not all the nodes, by the way. There is a chance you don't hear RTS and you don't hear CTS. يعني here RTX I receive it from a node that did not hear RTS and did not hear CTS of this current sender. لأن أنا remember here we're dealing with ad hoc. Ad hoc معناه إيه؟ We have a big network of nodes distributed everywhere, right? And any node can send to any node. In infrastructure-based protocols, all the nodes, they have to send to one central node. Even if we are next to each other, we have to send to the base station or to the access point. Okay? So in that case, some scenarios that we're talking about here is not going to happen. لأن إحنا كلنا, we are sending to one centralized node. But these types of scenarios are more valid in ad hoc. In ad hoc, we are distributed everywhere and anyone can send to anyone. So there is a chance that ongoing transmission may interfere with others and it may cause collision. Okay? That's why ad hoc is much trickier. That's why they did not, by the way, because of this particular reason, they did not allow device-to-device communication until 5G. يعني from 1G all the way to 4G, they did not allow any device-to-device communication at all, because device-to-device communication it creates many tricky scenarios, right? Because basically you are distributing the control. Yani the base station is giving away the control to the ad hoc nodes to send to each other without the engagement of the base station. This is very risky, because this particular transmission will in fact cause interference on the base station transmission, right? And many of these scenarios might happen in that case. Okay? So they did not allow it until 5G. And until today, by the way, it's not used systematically as part of 5G, as far as I know. Yani. Okay? طيب. The other class of MAC techniques is what we call polling mechanisms. In polling mechanism, unlike the reservation, polling mechanisms here, the arbitrator or the centralized node or the access point has to pull, in every time, has to pull the nodes in certain sequence, right? So with polling, there is always polling sequence. So assume that we have an access point and we have n nodes. The access point may choose to pull the nodes in certain sequence. Maybe round robin, which means one here, one, which means technically it's like TDMA, right? So if the pulling happens one by one, then it's essentially similar to TDMA, right? I may actually choose whatever sequence I want. So maybe node 1, I will pull it 2 times, and then node 3, and maybe node 2 will not be pulled in the sequence for a certain period of time, and so on. So, so if one terminal can be heard by all others, then this terminal is called the centralized node, or the arbitrator, or the access point, or the base station. All of these are names for the same thing. It's a designated node that controls the transmission. And in that case, all the transmission has to go to this node first, right? So if any two nodes, they need to have any conversation or to send data to each other, then one of them will send to the central node, and then the central node will send the transmission to the other nodes, right? So that's what typically happens in all infrastructure-based networks, whether Wi-Fi or cellular networks. All the transmissions it have to go to the centralized node first, and then from the centralized node to the other nodes. So we call it uplink and downlink. So if two nodes want to communicate, then that has to go through one uplink transmission to the base station and one downlink transmission to the other node. It has to go through these two phases. واضحة النقطة دي؟ طيب. So this terminal node, this central node is called the base station or the arbitrator or the access point. It can pull all the other terminals according to a certain scheme or strategy or a certain sequence. It has the full control to perform whatever sequence it wants. ماشي؟ So now all of these schemes, they are known as a polling schemes or polling sequence. So the randomly accessed polling here, the central node will pull the nodes randomly. Why? And does that actually guarantee fairness or not? Random, by the way, the random polling, it has certain advantages, right? One advantage is that if I actually pull the node in a certain sequence, then essentially what I'm doing is that I'm giving some priority to the beginning, to the first node, and I'm getting some I'm giving some lower priority to the node at the end, right? Because the node at the end has to wait for all these pollings until it gets the turn, right? So in a way, that's not fair. So I'm always in the beginning of the super frame, I'm pulling in the same sequence. So random here assumes that in certain frame, I can change the sequence, right? In a random way. So if I'm generating a random number, right, that gives me the particular node ID that I'm trying to pull at this point, this random behavior, by the way, is very fair. Why? Because if you flip a coin or if you try to generate a random number, right, chances are each node will take the first turn at different super frame, but on average it will be fair. So the sequence is different, yes, but on average each node will get its share of being pulled in the beginning or in the middle or in the end or something like this. And you will try this in the assignment many times. So actually in all the assignments, you have some random generators, and these random generators are actually pseudo-random, right? These pseudo-random generators, they guarantee fairness over a long time, right? So base station signals readiness to all mobile terminals, and terminals ready to send can now transmit a random number without collision with the help of the CDMA or FDMA. So what happens here is that the base station at the beginning of the super frame, it will wait for the nodes to give their readiness. Do you have data to send or not? Okay. The nodes will have to send their requirements based on TDMA or FDMA. So the base station, after this phase, will have the readiness from all the nodes. And then it has control back to pull the nodes in certain sequence that it finds appropriate. Okay? So if you do the polling randomly without querying or without waiting for the readiness from the nodes, then you assume that you have absolute fairness to all the nodes. But the problem with this is that absolute fairness is not good. Why? Why absolute fairness is not good, at least for networks? يعني.
Maybe there's different priorities.
هو مش different, ممكن يكون في different priorities وممكن هو different requirements. I'm watching مثلا high definition video on the TV, but you are browsing the internet. Somebody else is not doing anything. Somebody else is having a phone call over the network. We have different services. Our requirements are inherently diverse and different. So absolute fairness in that case is not really fair because it doesn't give each user what they want, right? Yes, so we always try to achieve what we call proportional fairness. Proportional fairness, not absolute fairness, right? So in some cases, I may choose to give a certain user two consecutive polling frame, or I give the chance to a particular node to send 2 frames consecutive, but the other node will send only 1. Why? Because at this point, this user is watching a high definition video, بينما this user is actually browsing the internet.
Here comes the concept of network slicing.
لا. network slicing لا. network slicing ده يعني network level mechanism. لا. Maybe you can give a seminar about network slicing in another. So network slicing يعني لا is a different. It's not in the data link يعني it's a network layer issue. ماشي؟
وقصده انه سلايس مثلا فيديو سلايس
يعني كل demand.
Yeah ما هو I'm saying services they imply a certain reservation mechanism or polling mechanism in the data link layer, right? The services up there they imply or they cause the fact that in data link layer you need to give proportional fairness and not absolute fairness. So what I'm trying to say is that the different polling mechanism for users, it has a particular reason, which is trying to give some quality of service. because the user who's making a phone call, they need some delay guarantees مثلا. And maybe كمان some reliable service in terms of error وكده يعني. They need low error. بينما الفيديو they need delay guarantees but they don't need reliable transmission. ماشي. Web browsing they need reliability in terms of error but they have no delay requirements at all مثلا. Best effort. There are some differences. These differences are required at the service level, but they imply certain protocols in the data link layer, right? They imply also some different slicing mechanisms in the network layer. They actually require different techniques and strategies at each layer. Here we are focusing on the MAC layer, ماشي? So in any case, so here the arbitrator or the base station will signal nodes ماشي to get their requirements, their readiness for transmission. And readiness for transmission معناها these nodes they want to send frames to the central node. Okay? Then based on these requirements, it has full control بقى to now it chooses one address for pulling from the list of all random numbers. So these nodes they send some random numbers, and here random numbers, by the way, these random numbers they kind of give some idea about the delay that they can wait to be pulled. So the nodes themselves they send some random number to the base station. If you have any transmission requirement, then you generate a random number and you send it to the central node. Why? Because these random numbers that you generate, it guarantees fairness. It guarantees fairness. Why? Because if a node generates sequence of random numbers, chances are some of these random numbers will be high and some will be low. So on average, the average will be the same, right? But this random number will make sure that the sequence of polling will be different at every time, right? So it's different at every time, so everyone gets pulled in the middle or in the beginning or at the end, okay, at certain points. But on average, we are all getting the same average. ماشي? So in that case, we have some fairness across all nodes, and we use what we call the randomly addressed polling. ماشي? The base station acknowledges correct packets. So if the base station, this happens, by the way, in uplink or downlink. So here, when you perform, so here the node will signal the central node, or the base station will signal all the nodes to get the requirements. If they have data to send, then they will send a random number, right? They will send a random number. This random number, as we said, it kind of represents how much time they can wait until they get the polling. They get the pull signal, right? In some cases, this random number will be very long or will be very short, or will be somewhere in the middle. But it represents how much wait time you can wait until you get pulled, right? So based on that, the central node will get all these random numbers, and then it does some mathematical derivations, and then it says, okay, so here I will pull node مثلا 1. Here I will pull node 1 again. Here I will pull node 3, and so on. Based on processing all these random numbers coming from the nodes. واضح كده? So these random numbers, as we said, it guarantees certain level of fairness. If we don't do this, then one strategy is to pull in the same sequence, صح? Over and over again. This is what we call حد عارف? This is what we call round robin. Round robin ده round robin guarantees absolute fairness. You have the same sequence over and over. It's like similar to TDMA in a way. ماشي? But the problem is that absolute fairness, as we said, is not always good. It's not always good because we have inherently we have different requirements, right? تفضل ماشي اوكي طيب اوكي another type of medium access control technique which is called inhibit sense multiple access. This type of multiple access techniques are valid for analog communication. يعني here remember AMS is first generation wireless. In first generation wireless we're dealing with analog communication. We're not dealing with digital communication at all, right? So how can we, again, if we have like walkie-talkies or something, and we are communicating with each other using analog communication, pure analog communication. So how do we reserve that channel? How do we control the access to the channel? So ISMA is one technique to do this, and ISMA here, the base station again signals on the downlink if the medium access is free or not. So if we use analog communication and we try to look at it in the frequency domain, there is like some frequency range for data transmission. Here, this one is for data transmission, okay? And there is some small frequency range for controlling the channel, because everything is analog, okay? So here we send what we call a busy tone. This busy tone indicates if the channel is free or busy. If the channel is busy, then we send a continuous, or actually the central node or the base station sends a continuous analog signal on the busy frequency range to indicate that the channel is currently busy. So no one can access the channel at this point of time. So if you try مثلا to click on the walkie-talkie to talk or to say anything, then it will not give you access, right? As long as this busy tone signal is there. Once you remove this busy tone, this means that the channel is now free. So any node can now send an uplink transmission to the base station. Once the base station listens to any signal coming from one of the nodes, then again it engaged in transmission with this node, and again it sends the busy tone on this frequency range to indicate that the channel is now busy. Okay, so whether uplink or downlink, we have to send this busy tone to indicate whether the channel is busy or not. This is the mechanism that we use as part of AMS or the first generation wireless communication, where we actually use analog communication. We don't use digital communication whatsoever. That's why we don't have the concept of frame ولا RTS ولا time slot وما فيش كلام خالص. Here we're dealing with analog communication, and we're dealing with analog signal in a specific frequency range. So that's a way of trying to reserve that in these types of systems or in first generation wireless. طيب we talked about اللي هو الcode division multiplexing as part of the physical layer. We want to here talk about code division multiple access, in which case بقى different nodes can use these orthogonal codes to try to perform communication at the same time. And as we said, with these orthogonal codes, we can send concurrent transmissions at the same time, and they don't interfere with each other. Again, using the concept of orthogonality. If these codes are orthogonal, then the correlation between any pair of codes is zero, and the correlation of a code with itself is very high, right? That's why when we multiply at the receiver by one code, we get the signal that has been coded with this code only, and we are able to extract it from the composite signal. ماشي كده? So in CDMA, all terminals they send on the same frequency and at the same time. ماشي? They can send at the same frequency at the same time, and we can still extract these communications from each other using the orthogonal codes. each sender has a unique random number, or the sender XORs the signal with this random number اللي هو الايه الكود. The receiver can tune into this signal or this transmission by using the same code at the receiver side. But احنا ذكرنا, we mentioned two conditions, two very important conditions on these types of protocols or transmission in order to guarantee that the reception at the receiver happens successfully. One is that, again, the power level of the transmission are almost equal at the receiver, right? So if we have two concurrent transmissions and the receiver or the receiving power on these two transmissions is almost equal, then we can extract one from each other normally. If one is very high and the other one is very low, then we may get some interference effect. So this is what we call the near-far effect. Okay, so the near-far effect is one of the problems of CDM or CDMA, and we have to guarantee that the power level at the receiver is almost equal between multiple transmissions. The other condition, which is also as important, is that these codes at the receiver and at the sender, they have to be synchronized or aligned together. Because if the code generated at the sender and the code generated at the receiver are misaligned, the correlation will not work. Okay? So we'll try this on an example now. We'll see that if the codes generated at the sender and at the receiver are not in sync, if they are misaligned a little bit, then the correlation will not work efficiently, and in that case, we will not receive the signal successfully. So this is one of the problems. So the other problem in CDMA is that the receiver is high complexity. Why? Because now the receiver has to maintain all the codes for all the transmissions that it wants to receive. So you have multiple transmissions happening at the network, and all these transmissions are happening at the same time, at the same frequency, right? But you want to extract one of them. If you want to extract one of them, then you have to have the code for this particular transmission. At different times, you may have to receive another communication, in which case you have to have the code for that transmission. So the receiver in general needs to maintain multiple of these codes, or many of these codes at the receiver level. And that, in fact, complicates the receiver design. The receiver design in that case, because it has to manage, and as we said, these codes, they have very large domain. Essentially, they can reach, if the key size is 32 bits, then you have a domain of 2 to the power 32 different codes. Okay, this is a very, very large domain. So imagine if a receiver has to deal with all these codes at the same time, manage this code, and know exactly which code it needs to use at any point of time in order to receive that particular signal. So that's why the receiver design is complex, and the signals should have the same strength at the receiver, which is the near-far effect, as we said. But in addition to this, also the codes have to be aligned, and we'll see now if the codes are not aligned, what will happen. But of course, on the other side, the terminals can use the same frequency. So in that case, even if we have multiple cells, by the way, even if you have a cellular system of multiple cells, we can still use the same frequency on all these cells. But as long as we're using different codes for these cells, and the codes are not conflicting from one cell to another, then we can use the same frequency. And they can all transmit at the same time. There's no issue. So there is huge code space, as we said, so that so any signal can be spread on the whole spectrum using the spread spectrum technique, using these orthogonal codes, and we have no issue with interference. So interferences, or the noise itself, remember the noise is in the medium, but the coding happens at the transmitter. the noise itself is not coded. So if a signal encounters some noise, because of the fact that this noise is not coded, then we can extract the signal even if there is some noise. And that particularly is facilitated by the fact that the codes are designed in such a way that the correlation of a code with itself is very high, and the correlation of the code with any other code is zero, right? So because the correlation of the codes with itself is extremely high, the noise cannot affect, and we'll see this using some numbers. And you'll be able to appreciate this by going through some examples with numbers. Another advantage is that forward error correction and encryption can easily be integrated. We talked about this. We said that these codes, in a way, they technically they sound like encryption or a coding technique for the signal. Sometimes these codes, right, they can be used also for error correction, right? Because if the signal is coded, sometimes if the signal has any error, which means that like one of the مثلا part of the signal or one bit flips from 0 to 1 or 1 to 0, not only we will catch it at the receiver side, but we'll be able to correct it. We'll be able to know the position of the error. And if we know the position of the error, we'll just flip the bit back, right? If the bit is 0, we flip it to 1. If the bit is 1, we flip it to 0. And then we corrected the error without having to go back to the sender. And that's particularly facilitated by the fact that the signal itself is coded. So this code, it has certain format, right? Because the signal is coded. It has certain format. So if this format is kind of, is different at the receiver, so the receiver may in fact be able to detect that there is an error, and it may be able to even correct the error as well. Of course, what we will explain later does not go into forward error correction, but forward error correction can be integrated seamlessly with the CDMA. And this is one of the advantages, okay? But we'll not go through this with the examples. Type, so we need to give some examples. So here we have the sender, and the sender A wants to send data. So the data of A is equal to 1 bit, and it's 1, right? And the sender has a key which looks like this, 010011, right? So the first thing that we should do for CDMA is to convert 0 and 1 into -1 and 1. Why? Why do we do this? Because if we talk about the correlation of this key with itself, as we said, the correlation of this key with itself, it should be high, right? So if we use 010011, the correlation or multiplying this key by itself, which means that I have 0 multiplied by 0 is 0, 1 multiplied by 1 is 1, and this is 1 multiplied by 1 is 1, and this multiplied by 1 is 1. If you sum all of them, it's a 3. So the correlation of this key with itself is 3. If we convert this to -1, if we convert the 0 to -1 and 1 to 1, by the way, I can do it the reverse. So 1 will become -1 and 0 will become the 1. It doesn't matter. But if I do the coding this way, right? If we try the same example now, if I try to get the correlation of A with itself, then it becomes a -1 multiplied by -1 is a is 1.
It's 1. It will be back to 1.
Yes, and 1 multiplied by 1 is a 1. And all of these will be 1. So the correlation will be 6, right? So not 3, but in that case. So we code the 0 to -1 in order to increase the correlation of the code with itself. So when it becomes 6, then the noise will not affect it. If you have any noise can drop the 6 back to 5, to 4.5. It's still, for us, it's still positive, so we consider it 1, right? We'll see now how to interpret at the receiver the bit, at the receiver side. So if it's above 0, it's 1. If it's below 0, it's 0. خلاص. So because the correlation is very high, as long as it's above 0, it's 1. So if it's 6, chances are if there is any noise, it will drop to 5, to 4. It's still above 0, way above 0. So we know that the bit is confidently 1. So this is the motivation behind converting the zeros and 1 to e to minus 1 and 1. Is to increase the correlation of the code with itself. Okay? Right. So assuming that B wants to send data, and this data is 0, and it has this code. Of course, if you multiply this code by this code, you will find that if you multiply this by this, the answer should be 0. Right? If you multiply this by this, the answer will be 0. And if you multiply this by itself, the answer will also be obviously 6. So all the codes, if you multiply it by itself, the answer is 6. And if you multiply it by any other code, the answer is always 0. ماشي? So if B wants to send 0 over the channel, it will first convert this 0 to minus 1. It will convert this code to 1, 1, minus 1, 1, minus 1, 1. And then it will multiply. So if we multiply the data by the code, so this is the answer. If we multiply the data, which is 1, by the code, this will be the answer. And then when you send, and assuming that you're using equal transmission in such a way that at the receiver they will be at the same level, so ideally what you receive at the receiver is a signal that looks like this. In the ideal case, طبعا. Of course, it's not exactly like this because there is some kind of attenuation, ups and downs. So assuming the ideal level that at the receiver side, we will have the composite signal, which is the summation of AS and BS. So we will have a signal that looks like this. Minus 2, 0, 0, minus 2, 2, and 0. So that's the composite signal that we will receive at the receiver. So now, from this composite signal, the receiver can use either AK or BK in order to receive the signal. So the receiver wants to receive the signal from A, in which case it uses AK, right? So if I use this signal and multiply it by AK, so we multiply this minus 1 by 2, it becomes 2. We multiply this 1 by 0, it becomes 0, and so on. And we keep doing this. So the answer is 6. So 6, in that case, is way above 0. So we know that since this is above 0, then the original bit is 1. If this is below 0, then the original bit is 0. Right? So this is basically the sequence. If we want to receive B, then we multiply the composite signal by B, and the answer is minus 6. So see the difference? Now it's there is big discrimination between the above 0 and minus 0. So correlation is very high, and it gives you confidence that the bit is 1, or the correlation is minus, and it's also very high, in which case you have confidence that the bit is 0. So even if there is some noise effect, you can still recover the bit easily. Of course, this example is a happy path. Of course, it's not as easy as this. So this is a slightly more complex example. In this example, D wants to send like a sequence of zeros and ones, and just to keep you a little bit confused, here the 1 is coded as minus 1, and the 0 is coded as 1. ماشي؟
For more correlation.
لا هو here when you flip it doesn't matter. So as long as you're consistent, ما تقوليش أنا هستخدم I will use the one here as minus 1, but after some time I will use it. You have to be consistent. ماشي؟ The idea here is that in general A uses a digital signal that looks like this. ماشي؟ And the key is a continuous code. And if you see even here, this key at this time is different, but this key is continuous over time. Okay? And if you have the key for A and the key for B, it's always orthogonal. If you multiply any two keys with each other, the answer will always be zero signal, right? But the key is continuous. ماشي? So this is very important. And the other thing is that if we want to guarantee successful reception at the receiver, this key has to be synchronized with the key generated at the receiver. This is very important. And we'll see now some example where if they are not aligned or if they are not in sync, the correlation will drop down and it may cause some confusion at the receiver, and the receiver will not receive the signal successfully in that case. ماشي كده؟ طيب. So forget about this. This part is not important. What this tries to say is that even if we're dealing with zeros and ones, we can still use XOR in that case. We use XOR in that case, and the answer will be the same. But yani forget it. So we deal with the binary signal like this, and ones and minus ones, and the correlation is higher in that case, so it will be easier. تفضلي.
How the codes are spread through the senders and the receivers? How they have all the code is in the hardware or?
So these codes it can be generated from a domain of codes. As we said, if the code length is 32, you have a big domain of 2 to the power 32. But the issue here is the question is valid. How to manage these codes? Who will get to use this code at certain point of time? This is managed by the base station. The base station has to manage which codes can be used by particular nodes to send. ماشي?
If I have a mobile.
Right.
And there is a base station.
You can generate these codes at the mobile level. There is no issue with this. You know this, right? These codes are well known. Yani these codes are not. يعني the sequence of ones and zeros for this code can be generated. It's based on something called Hamiltonian, if you know. It's based on some Hamiltonian matrix, and this Hamiltonian matrix can be generated by anyone. It's just a very simple algorithm, right? That you guarantee that if the code is 32 bits, مثلا, the Hamiltonian matrix can be generated using this algorithm. It's very simple, يعني. ماشي? But so the mobile station can generate this code locally. But the problem is that which code should I use at this point? صح? Am I answering your question?
Okay, I should have only unique ones.
صح بالضبط. Okay. So which one I can use at this point? This is managed by the base station. So the base station tells me. Okay, you have all the codes, but you can use this one at this point of time. واضح? So the control is always done by the base station, and that has to go through coordination between the cells, right? Because you have multiple, you know that, صح? You have multiple cells, and each cell is you have a base station, right? And even from one cell to another, right? You have to coordinate between these base stations, right? Because you have like some frequency planning, you have code planning that has to happen. So if one cell uses a certain frequency range, the other cell should not use that range. If one cell uses certain subset of codes, the other cell should not use that subset of codes, right? Otherwise, the near-far effect will happen so often, and you will not be able to and you go through interference, and you don't want to go through these issues. واضح كده؟ So the codes, they spread the signal. As you can see, the code has higher frequency, صح? So the codes, they spread the signal on a higher frequency range. That's why we call it spread spectrum. It spreads the signal. So in any case, the signal at the end of the transmitter, A, okay, will look like this. So -1 multiplied by 1 is -1. Right? And -1 multiplied by -1 is 1, and so on. You keep doing this. So this is how the signal looks like, and it's also continuous, right? It's also continuous. So this is AS. So we'll take back AS in the next slide with BS and try the same thing.
Why
Yeah, ما هو that's what I'm saying. يعني from one bit to another, you don't have to use the same code. هو the code is continuous. Sometimes they don't want to repeat the code so that at every bit you have a change of signal, and this is actually good for. Sometimes it's used for detecting the beginning and an end of a particular bit. It's used for, it enhances the synchronization يعني. So that's why here they don't want to use the same key over and over and over again. Okay? So the key is continuous, and the most important thing is that if you multiply this key at any point of time, at any bit, with any other key, whether بقى BK or CK or DK or something, it's orthogonal, which means that the correlation is zero. ماشي? We call this chip sequence. We call it chip sequence. So this key, we call it chip sequence. So we can generate this chip sequence with certain sequence at the sender and at the receiver. ماشي؟ اتفضل. So this is the signal that we generated from the previous slide, and B will have the same thing. Of course, in that case, the sequence of bits is different, right? So what this example tries to say is that this is not applied to only one bit. So we can generate as many bits as we want, and we can still get it recovered at the receiver. So if BK looks like this, so BK is here is 0, 0, 0, and then 1, 1, and so on. Of course, we don't have to deal with this again. You can forget about this. مش مشكلة. ماشي. But the sequence always applies. So here, -1 multiplied by -1 is, sorry, here, signal, so sorry, -1 multiplied by -1 is, sorry. This is signal A. So here is B, okay. -1, sorry, -1 multiplied by 1 is -1. ماشي? And then -1 multiplied, and so on. So this is the signal of B. This is how it looks like. So if you get the summation of this, so here this is -1 and this is -1, so the answer is -2. So here, remember, this is actually -2, and this is 0, and this is +2. Okay. Here بقى we're dealing with absolute voltage levels, so we get the summation of all of them. ماشي? So this is the composite signal that hopefully the receiver will receive. Again, in ideal case, of course, it will be plus or minus, but the ideal case is that the receiver will receive this signal, this composite signal, right? So if we multiply بقى the key of B multiplied by this composite signal, we're supposed to get this signal back. If we multiply AK, we'll get the signal of A, and so on. ماشي? So if we assume that this is the AS plus BS, and we multiply it by AK, so what happens here is that, again, we multiply, this is -1, this is +1 multiplied by -2. So the answer is -2, right? And this is a 0 multiplied by -1, so the answer is 0, right? And so on. So here, again, this is -2, this is 0, this is +2. ماشي؟ طيب, at the receiver بقى, what do? We use, in general case, we use what you call an integrator. There is like an integrator circuit كده. Some of you have studied this in digital logic or computer architecture. You have an integrator circuit that tries to sum the signal levels at every bit. So here, for example, we have here the signal level is -2, so we have a -2. So this goes to -2, right? And then we have 0, so the signal stays the same. And then we have -2 again, so we go down. So this is -2. And then we have -2, so we go further down. So this is the integrator. It kind of accumulates the voltage levels. واضح كده؟ واضحة ولا مش واضحة؟ So we go -2 and then 0, and then يعني stays the same, and then we go -2, so this is -4, -6, and then this is 0, so it stays the same, and this is a -2 again. So Here we reach to -8, which basically it's below 0, so the original bit is a 1. Remember, it's 1. واضح? And we do the same بقى for each particular bit, and we can see that we recover the same signal of A using the concept of A integrator يعني. And again, this integrator tries to calculate the correlation, ماشي? And if the answer is above 0, then we assume it's A. It's 0. If the answer is below 0, then we assume it's 1, depending on the coding that you have used at the beginning. واضح كده؟ طيب. If we want to recover B, we do the same example. There's no difference here, and we get the value of B. More importantly, if we use a wrong key, this wrong key might typically happen by the fact that the key generated at the receiver is only shifted by 1 bit, by just 1 bit. ماشي? So if it's shifted by 1 small bit, that conflicts with the orthogonality completely, and that's one drawback of CDMA. It's actually a drawback, but we will see. We'll use it for our advantage in a bit. So if we're using a wrong key, then we can multiply again -2 by 1. The answer is -2, and 0 by 1 is 0, and so on. If we use by the integrator, let's see. Here the integrator will go -2, and then we stay the same, and then we go a +2. So we go back to 0. And then we go positive. And we stay the same, and then we go positive. So يعني that's in a way, خلاص, if it's above 0, يعني we can say that it's 0. Fine, it's okay. Maybe there is some noise, things like that. And يعني we can, although this might be a mistake. This might not be correct. ماشي? But you can end up with a situation like this. So the integrator will go negative here, will go negative, and then 0, 0, 0, and then it will go positive and 0, 0. So here, what is the bit? I don't know. And of course, for typical reception, we use a certain threshold, which should not be 0. يعني it should be plus or minus. We sometimes يعني account for some noise floor or noise effect. So the threshold is typically not 0. Sometimes it's slightly positive, slightly negative, things like that. ماشي? But here, you cannot tell. Okay? And that wrong key might typically happen just by shifting 1 bit, the key at the receiver. بس misalignment صغير بس might happen. ماشي? So the synchronization, the alignment of these keys is very important.
And they are not randomly generated like...
لا, they are not randomly generated, of course. There has to be, يعني, they are generated based on the orthogonality, as we said, based on, I don't want to يعني, go into details, but they use the Hamiltonian matrix والكلام ده. And yes, they have to ensure, more importantly, they have to ensure that they are synchronized. This is very important. طيب, في بقى technique بقى very interesting. It's called the spread ALUHA multiple access. Okay? So the idea here, this is in fact used for some ad hoc communication, like wireless sensor networks and stuff like that. So the idea here is that we know that ALUHA is very attractive as long as the network load is low, right? And it's good for multiple access because you will see this in the assignment, in the next assignment, that until the probability of collision is high, ALUHA is very good because it keeps opportunistically accessing the channel with good efficiency. But the problem is that once we get to a certain network load, we start to get some collision, and ALUHA does not have any effective technique for dealing with the acknowledgement. ماشي? On the other hand, we have CDMA. It's attractive. It's good. We don't have collision in that case. We don't actually have collision, right? We eliminated collision altogether by dealing with the high domain of codes, and it's very attractive. But the only problem with CDMA is that the receiver design is complex because we have to deal with high domain of codes, large domain of codes. Okay? طيب, so how can we get the benefit of both? We're trying to get some trade-off. So this technique is interesting. This technique tries to say, okay, so let's use Aloha. Aloha allows the nodes to transmit asynchronously, right? Asynchronous. They can transmit at any point of time. Remember, in CDMA, they transmit at the same time, at the same frequency, صح? Here, Aloha does not, Aloha uses the asynchronous communication. But the problem is that if we use asynchronous communication like this, right, we may end up with some overlap between these frames, in which case we have collision, right? So what can we do here? They tried to use CDMA, but CDMA uses multiple codes, so we can say that we can use one code for A and one code for B. لا, they don't do this. Interestingly speaking, they use the same code for all nodes, which drops down the complexity of the receiver drastically, صح? So here, the receiver can deal with only one code. But there is only a slight glitch here, is that the alignment of this code has to synchronize with the key of the node that you are trying to receive the signal from. This is the only thing they need to do. Okay, so we use one code, okay, and we use Aloha, right? So this sender A will use one key, ماشي? It's one key for the entire system, ماشي? But this key here, the key is this blue one. So the key has certain value, I think is 110101. So here the signal will be 110101. So this part here. Okay? And B uses the exact same code, but it's actually generated here. So here will be, so this is 0, so it will be -1, -1, 1. So it's the reverse, okay? So this is AS and this is BS using the same code, but they are slightly misaligned. Slightly misaligned because Aloha allows for asynchronous communication. ماشي? So this is AS spread, ماشي? And BS spread, and there is overlap between them. So there is overlap, right? So in that case, the receiver can align the same code, one code for the entire system, but it can align with the sender A to receive the signal from A, or it can align with this with B if it wants to send or to receive the signal from B. Because as we said before, if the key is misaligned, the correlation خلاص, it doesn't happen. The orthogonality condition will not be valid. So as long as there is some partial overlap, right, there's no issue. The receiver can synchronize the key with the sender and can still receive A or B by using one code.
And Doctor, this code through the time, it is all orthogonal.
Yes, of course. لا ما فيش بقى هنا orthogonality applies when the code multiplies by any other code. هو one code في السيستم كله. فهو الفكرة ان هو الكود عشان الميس الاينمنت فصار في ايوه، لان هنا احنا essentially what we do is that we spread the signal using the code. You see here, like this code has spread AS and has spread BS, but there is overlap, واضح صح؟ But I can still extract AS from BS because of this spreading, okay? And by aligning the code at the receiver, I can extract A from B or B from A by aligning the code with A or with B, okay? طبعا the other one, by the way, is not totally orthogonal, and it will form some kind of interference, right? But again, because I'm aligning with one node, the correlation with this node is very, very high. So the interference will not affect this high correlation. ماشي? The only exception is when A and B, they send data at the exact same time. صح? in that case هتالاين مع مين بقى؟ كل سنه وانت طيب خلاص. And this is a case of collision بقى خلاص.
بس البروبابيلتي يعني so
البروبابيلتي ايوه الله ينور عليك صح. The probability here is very low because Aloha assumes asynchronous communication. ماشي. So as long as there is partial overlap, using one code I can still recover the signal, which is a beauty بصراحة. This is very nice. طبعا the other signal can still introduce some interference, but with the high correlation I can get around this. مفيش مشكلة. So in that case I lowered the complexity of the receiver, right? And I used asynchronous communication. Aloha is very simple. Aloha, by the way, is very simple. So this technique here, it has big advantage that it's very simple. I'm using one code and I'm assuming asynchronous communication. خلاص. ماشي? But did I eliminate collision altogether? No. No, I cannot say that. Because if the overlap is very major or they are identical, no. It's not interference in that case. It's collision. It's complete collision. واضح ولا في أي
Also,
confusion?
the length of the code should be greater than or record the longest message that the sender can send.
هو assuming here the frames are equal size.
Oh, they are
The frames are equal size, but they are sent at different times. Because if they are sent exactly at the same time, then the overlap is complete, is 100%. In which case, using one code will not help. You have to use multiple codes in that case. And the complete overlap, we call it in that case collision. It's not interference. خلاص. It's collision. ماشي كده؟ طيب, this is the last slide for this chapter. So of course this is only a comparison between the اللي هي non-collision techniques. So this is a quick comparison based on the 4 different domains that we talked about, whether the spatial domain, the time domain, frequency domain, or the code domain. So this is the idea. So the advantage here is that SDMA is very simple. It relies only on directional antenna. That's it. So we talked about this. But it increases the capacity per kilometer using the sectorized cell. We talked about the sectorized antenna and the fact that a cell can be, in fact, divided into sectors, in which case each subcell can support multiple users. Okay, I'm trying to create assignment 3 where you can discuss the performance of this as well. Hopefully, I will succeed. طيب, ال TDMA of course is simple, but it needs again some synchronization for the beginning of the frames. And the disadvantage here is that we need some guard bands to avoid the missynchronization, and we also can waste resources, because if we assign a node if we assigned a time slot to a node and the node doesn't have any data to send, so we are wasting resources in that case. ماشي? But it's very simple, similar to FDMA. FDMA, one of the disadvantages is that, of course, because of the inflexibility, by assigning fixed frequency range for domains, also we are wasting resources, and also the sender and the receiver, they need to support multiple frequency ranges. So in that case, the transceiver also is a bit complex, because it has to send data in different frequency ranges, and that also complicates the design of the transmitter and the receiver. CDMA, we talked about it today and several times. We said that in terms of advantages, the code domain is very large. It's very attractive. It's used as part of 3G. We'll study 3G in details, starting maybe 2 lectures down the road. And the disadvantage, of course, is that it's very complex. Receiver design is complex, and we have to deal with issues like the near-far effect and the alignment of the key generation at the receiver side. ماشي? So these are the advantages and the disadvantages. Okay, so this is, I think, the end of this chapter. So inshallah, next time.